So for this video, we're going to go through the Chapter 13 worksheet that describes what a sampling distribution is. So before you view this video, you want to go through the slides that are provided in Blackboard. So we're going to be looking at all the apartments listed on Airbnb in 2016 in New York City. So if you go to StatCrunch, click on Data, and you look up Stat 141 Airbnb, and this will be the one that pops up, and this is the one we're going to look at. And so this data set's a little unusual in that we have the entire population's information, which usually you don't have on hand. That's kind of the point of statistics. Is we're going to go out, we're going to take a sample from a population and then try to learn about the parameters from the sample that we have. So we're going to learn about the population through the sample, we're going to learn about the parameters through the statistics. So what Chapter 13 is going to be about, at least the sampling distribution part anyway, is we're going to kind of flip what we usually do. We go out, take a sample, try to learn about a population. Instead, we're going to learn if we actually know about the population, what sort of samples can we expect to get. If instead of just taking one sample, if we took thousands and thousands of different samples over and over and over again, what would those sample proportions and sample means look like? What can we expect to see? So if you flip a coin 1,000 times, it's possible that you get 0 heads or 100 heads or 1,000 heads. It's just not very likely. You're going to get probably something close to that 50% mark. And we're going to be doing the same thing, but we're going to be looking at all of the apartments that were listed in Brooklyn. And so those are the ones we're going to focus on for this video. So the very first question wants to know is, what proportion of all apartments are located in Brooklyn? So we're actually able to get a parameter. And so that's something we're usually not able to find, is the exact value of the population proportion. So where the apartment is located is a categorical variable, and our population proportions for categorical variables use the letter P. So anytime we're dealing with a categorical variable, we're going to end up using a proportion. Since it's the proportion of all apartments, we're able to calculate a population proportion. So we're going to go back to StatCrunch. We're going to go back to StatCrunch and find what proportion of all of the apartments happen to be located in Brooklyn. So what we can do, we go to Stat, Tables, because we're dealing with a categorical variable, and Frequency. We want to look at the neighborhood group. And if you notice, it's going to give us the frequency and the relative frequency. Your frequency is the count, the actual number of apartments located in Brooklyn, and then the relative frequency is going to give us that proportion we're looking for. And then if we click Compute, it spits out the 5 major boroughs in New York City. And we can see for Brooklyn, there are 16,668 out of a possible 4,429. So we had 16,680 over our total, which we can find here, our count of 40,429. Which will give us a population proportion of exactly, we'll round it off and say 41.2%, 0.413. So the idea is, if we didn't know the entire data set, we would just go out and collect a sample of apartments, we would want to try to estimate this proportion here, this 41.3%. So what we want to try to do is we want to try to figure out what's the probability that a random sample of 10 apartments would have 50% or more located in Brooklyn. And unfortunately for us, we can't quite do that yet. So what we would have to do is find every single apartment, every single sample of 10 apartments you could get, and count the percentages that had 50% or higher in Brooklyn. So we can't do that quite yet. So instead, what we'll do is we'll just simulate it. We'll just take a sample over and over and over again. So if we go back to StatCrunch, we can get StatCrunch to take a sample for us. If we go to Data, go down to Sample, we can tell it what variable we want. We want our sample size to be 10, and we can even tell it how many samples we want. So for right now, let's just take a sample of 1, and if we click Compute, it'll give us the randomly 10 picked apartments from this entire column. And if we count, we have 1, 2, 3, 4, 5. 5 apartments in Brooklyn. So we have 5 apartments in Brooklyn out of our 10, which will give us a sample proportion of 5 out of 10, or exactly 0.5. So our first sample gave us a sample proportion of exactly 50%. Well, if we want to try to figure out how often we'll get a sample proportion of 50% or higher, we have to do this not once, but many times. So let's take 2 more samples. And the idea is, since we're pulling these apartments at random, every time you take a new sample of 10, you'll likely get 10 new apartments that would be located in different areas. So every time you take a new sample, you'll get a different sample proportion. So we're going to kind of treat these sample proportions like they're a random number. And what we did in chapter 12 is we try to figure out a probability distribution, or a probability model we can create for these random numbers. So let's do it again. Let's take another random sample of 10 apartments. So we can go back to Data, Sample. We're going to do it two more times. So we want a sample size of 10. We want to pick it from the neighborhood group, and we'll tell StatCrunch that we want 2 more samples. Click Compute. And for the second sample that it took, we had 1, 2, 3 apartments in Brooklyn. So our second sample proportion is 3 out of 10, or 30%. So that's somewhat far away, right? The actual population proportion is 41%. The sample gave us a sample proportion of 30%. Not that accurate of a result. If we look at the third sample that we have 1, 2, 3, 4 apartments from Brooklyn. So 4 out of 10 gives us 0.4. So 3 different samples, 3 different results. It's possible that if you take 3 more samples, they all give you the exact same sample proportion. But that's the main idea. If you go out and you take a new sample, you'll get different apartments, you'll get different sample proportions. So what we want to try to do is figure out, what are all of these different sample proportions going to look like? How often will I get a sample proportion of 50% or 30% or 40%? Or, it's possible if you pick 10 apartments, all 10 of them come from Brooklyn, or none of them come from Brooklyn. So how likely is that to happen? So we're going to simulate it, and simulating it one at a time could take a very, very long time. Fortunately, StatCrunch is going to let us speed that up. So what we can do, we can go to Applets, Sampling Distribution, Binary, and enter the population proportion, and we'll have it take 5,000 samples for us. And there's going to be 3 things we're going to want to note about these 5,000 samples. We're going to treat them like we would a quantitative variable, because we're getting sample proportions and those are numbers. And we're talking about quantitative data, there's usually 3 things that we want. The shape the data takes, its center, what would we typically expect to get, and its spread, kind of how far away from the center can we reasonably expect a sample proportion to be. So where do we get those in StatCrunch? So we want to go to Applets, all the way down to Sampling Distribution. We want a binary. Binary means 2. In our case, our apartments either are in Brooklyn or they aren't, so there's 2 outcomes. And we just want to figure out what's the probability of getting an apartment from Brooklyn, or what's our population proportion of all apartments being from Brooklyn. We found that to be 0.413. And then if we click Compute, it's going to give us a layout that's going to look like this. At the top is the population data. If you notice, there are 2 outcomes, 0 if it's in Brooklyn, not in Brooklyn, 1 if it is. So this has a height of about 0.6, this has a height of about 0.4. And if we tell it we want to take a sample of 10, what it's going to do is it's going to pick 10 apartments at random. So it happens that 6 of the apartments weren't in Brooklyn, and 4 of them were, so we end up with a sample proportion of 40%. So it's going to drop a little bar down here. And we can see that the mean of all of these sample proportions down here is 40% right now, because that's our only one. And I'm not going to be able to calculate a standard deviation quite yet, because you can't calculate a standard deviation if you only have one outcome, or one statistic in this case. So if we click one more time again, repeats the process, picks 10 apartments at random. In this case, only 2 of them were from Brooklyn. So we end up with a sample proportion of 20%, creates a little bar down at 0.2, and then now if you average the 2 out, you get 0.3. We want to do this over and over and over again. So let's do this about 5,000 more times. So StatCrunch in an instant took 5,000 samples of size 10, and so there's going to be 5,000 different samples represented here. Not 5,000 different apartments, 5,000 total samples, and each sample has a size of 10. So essentially, this histogram down here has 5,000 different sample proportions. If you notice, it has a little bit of an upper tail, and it's centered right at the population parameter, right at our population proportion of 41.2%. So we can kind of see a bit of a pattern. Our most likely outcome is to get a sample proportion of about 40%, but you don't always get 40%. The next 2 most likely outcomes are about 30% and 50%. Then as you go farther and farther away from the center, from that 41%, the chances of getting that sample proportion grow smaller and smaller and smaller. But you can get anything from 0%, that happened occasionally, all the way up to 100%. That happened very seldomly, but it did occur. So you can get anywhere from 0 to 100%. So if we look at it, the shape is about bell-shaped. It has a little bit of a right skew to it. So if we put in the shape, it's slightly right skewed. Which, what we're going to want to end up doing later is we're going to end up using a normal model to kind of mimic the shape that these sample proportions take. And if they're right skewed, a normal distribution isn't going to give us really that accurate of results. And then I want to know if from these 5,000 samples, on average, what sample proportion did we get? And all of them miss, all right? You can't get a sample proportion of exactly 41% if you only take a sample of 10 apartments. But even though all of our sample proportions were wrong, if you kind of combine them together, if you see how well they perform as a group, total, they give us exactly what we want, right at our population proportion of 41.3%. It's just very slightly off. So the average, or the center, of all of those sample proportions, of all 5,000 of them, is our population proportion of 0.412. And that's what it means to be unbiased. In Chapter 10, we talked about we take random samples to avoid bias. And that means that even though your statistics are going to be wrong, as a whole, as a group, they're going to be right on target, even though each individual one is likely to miss. And we can kind of estimate how much they miss by calculating the standard deviation of all these sample proportions. On average, how far away is a sample proportion going to be from the truth? And the larger the standard deviation is, the less accurate our sample proportions are, the less we can really trust them to give us an accurate result. So in this case, if you kind of round it off, your typical sample proportion is off by about 16%, which is a pretty large error rate. So the standard deviation is measuring our sampling variability, or our sampling error. Every time you take a new sample, you get different samples, so you get different statistics, and they're changing by about 16% every time you take a new sample. And it's going to be about off from the population proportion by about 16%. So we're going to include that for our spread. So we call this the standard error. Variables themselves have standard deviations, but when we talk about statistics, we kind of change it from a deviation, how much it varies from the average. Now we're going to talk about how much it varies from the parameter, or how much it differs from the parameter. So the standard error, on average, what's the error in our estimation? In this case, worked out to be about 0.156, or right at about 16%. So if we didn't know the population proportion, we could be off typically by about 16%, and if you look at all these sample proportions, it's not unusual to get something as 20%, or even high as 80%. So if I didn't know that 40% of apartments were in Brooklyn, and I took a sample, it could get a sample proportion of 80%, which would give me a very wrong idea. It may lead me to have the wrong conclusion. So when you have these high standard deviations, when this sampling error is high, you can't really trust your sample statistics. You had a question at the very beginning of what are the chances, if you just take a random sample of 10 apartments, that you happen to get 50% or more of them in Brooklyn. So what we can do is we have 5,000 samples. Let's just see what proportion of all of these samples we collected are at 50% or higher. And we can do that using StatCrunch. If you come down to this little option box down here, it'll let you click on dividers. We want percents. And if you click OK, you can change this to be whatever you want. So if we click on this little arrow, we can change it to 0.5, which is what it defaults to. And you can see that about 39.5% of the time, we ended up with a sample with 50% or more Brooklyn apartments in it. So from our sample, we end up with the probability of getting a sample proportion of greater than or equal to 50%. That happened, a little bit less than 40% of the time. And what we want to do is eventually replace this distribution down here with a normal distribution. So let's see. We have a mean, we have a standard deviation, that's all you need to use a normal model. So let's figure out what the proportion would be using a normal model at 50% or higher. So if you haven't already, you want to bust out your calculator. And what we're going to look for is we'll draw our normal curve. It was centered at about 0.41. And then if we go up a tick mark by about 16% each one, we'll have one tick mark up here of 0.157. Then another one at about 0.73. And then at about 0.25. And then at about 0.09. We draw our normal curve out. And we want 50% or higher. That's going to fall somewhere between 41 and 57. And we want more, so we'll shade the right. So this is the part we want to find. We'll go to our calculator, turn it on, go to second vars, and then scroll down to normal CDF, enter in 0.5 for our lower bound, because that's where we start shading, our upper bound of some large positive number. From our sampling distribution, we found the mean to be 0.412, a standard deviation of 0.156. And if we had enter according to a normal model, that would actually be about 28.6%, a much smaller percentage than the actual real answer that we got from our simulated one. So our theory, this theoretical model, doesn't match the reality. They're a little bit off. So using a normal model to mimic our sampling distribution didn't do a good job. So how can we go about fixing that? And a lot of the problems in sampling can be solved by taking a larger sample. Larger samples won't make it unbiased, but as long as you're taking random samples, if you take a larger sample, it'll fix a lot of issues. So let's see what happens if instead of taking a sample of 10 apartments, we take a sample of 40 apartments. What is going to change about these three characteristics, the shape, the center, and the spread? So what we can do is we go over here to sample size, change this to 40, and we can do it again. Now if we pick one time, it's going to take a random sample of 40 apartments from up here. This time we end with a sample proportion of about 42.5%, so it places a little bar at 42.5%. Do it again. This time ended up with a sample proportion of about 35%, so it places a bar at 35. If you notice, the first two were pretty close to the true proportion of 41%. We don't want to do it 2 times or 3 times. We want to do it 5,000 times. 3,000, 4,000. And if you notice, the proportions got a lot closer to the population proportion of 40%. So let's make this a little bigger. It got closer to the population proportion of 40%. It wasn't unusual to get a sample proportion of 20% or smaller, or 80% or higher with only a sample size of 10. Now, it never had a sample proportion of 80% or higher, and it very rarely ended up getting a sample proportion of 20% or lower. So the range of sample proportions we can expect to get got a lot smaller because we took a much larger sample. And not only did it make the range shrink, it also made the shape much more normal. And if you notice, we don't really have a slight right tail like we did the first time. So, if we go about describing our 3 characteristics, the shape is much more bell-shaped. So that's the first thing we kind of want to note, that it's bell-shaped. And then we want to try to figure out is, most of these are probably going to be wrong, probably not going to end up with a sample proportion of exactly 41%, the population proportion, but as a group, how well do they perform? How close do they get to the target of 41%? And if we average all of these out, we end up with a population average, or an average of all of our sample proportions right at the population proportion. So again, we took a random sample, we ended up with an unbiased result. And when we get to the next one, that's what you'll see as well, is that as long as you take a random sample, the mean of all of your statistics are always going to be the parameter they're trying to estimate. So the center is still the population proportion of 0.411. And then the next thing we want to know then is, as a group, they perform really well, they hit the target, but with a sample size of 10, as a group, they performed well, they hit the target. But we don't take 5,000 samples, we take 1. So how do they perform individually? We just go out and take 1 sample. How trustworthy is it, or how accurate is it going to be? So we come down here to the standard deviation. This time we're off by about a little less than 8%. So we went from off by about 16% down to 8%. So taking a sample size of 40 kind of cut our error in half. So the error in our estimation gets smaller as you take a larger and larger sample. You can trust them to be closer to the truth when you have these larger samples compared to the smaller samples. And we noticed that at the beginning when we talked about how much less spread out they were. Our sample proportions were much more consistent the larger a sample that we took. So our new standard error for a sample size of 40 is about 0.079. So let's see it again. I want to know, if we take a sample of 40 apartments, how often will we end up getting a sample proportion of 50% or higher? So this didn't change, it's still at 50%, and we can see now it happens 16.3% of the time. The larger sample you take, the less likely you are to get something somewhat far away from the population parameter. Our statistics get closer, they shrink in closer and closer to the parameter, so the chances of getting a sample proportion above 50% went down. The probability of our new sample proportion being greater than or equal to 50% is now 16.3%, or 0.163. So let's try our normal approximation again. So we draw out our normal curve, centered at our population proportion of 41%, but now our standard error is about 0.08. So our first tick mark will be at 0.49, and our second tick mark will be at 0.57. We're still looking at 50%, which will be really close, just barely past this 49. We still want above, so we'll shade to the upper area. So if we go to our calculator, go back to second vars, scroll down to normal CDF, We have a lower bound of 0.5, an upper bound of 1,000. Those didn't change. Still looking at the chances of getting a 50% or higher proportion. The mean stayed the same when we increased our sample size. The difference is that the standard deviation got smaller. So we're going to change this to 0.079. And we end up now with a chance of about 13.3%, which isn't exact. Our simulated gave us 16.3%. Now we end up, from our normal model, with 13.3%. They don't give us exactly the same, but we don't really expect a normal to do it. That's why we call it an approximation. We don't expect them to be exactly the same. But if I didn't know it was 16% and I thought it was 13%, I'm wrong, but I'm not that wrong. It gave me pretty close to the truth. So what they say is you need 3 attempts to really make a pattern. So let's do it one more time. Let's up our sample size from 40 to 1,000. So we'll change our sample size from 40 to, not 1,000, 100. We'll take a sample of 100 apartments this time. Again, if you click one time, took 100 apartments, got a sample proportion of 40%, dropped down a marker at 0.4. Did it again, took a sample of 100 apartments. This time we ended up with a sample proportion of 35%, so places a marker at 0.35. So let's do this 5,000 more times. So we end up with a total number of samples. Again, these aren't the number of apartments in our sample. These are the number of samples, and each of those 5,000 samples has 100 different apartments inside of it. You can kind of think of these as like a Russian nesting doll. The overall doll has 100 other dolls inside of it, and we have 5,000 of these different big dolls. And from each one of those samples, each one of those Russian dolls, we calculated a proportion. And if you can see this time, the sampling distribution got even closer to the population proportion of 41%. Larger samples, less spread, you get more and more consistent results. Now it's very, very bell-shaped. So if we write down the shape that it takes, it's very bell-shaped, meaning that a normal model should give us a really close approximation. We can kind of draw that bell curve on top of it, and we can kind of use the normal model instead of these 5,000 different samples. But to use a normal model, we need to know 2 things. We need to know what its mean is. So again, if we averaged out all 5,000 sample proportions, we end up with an overall average of all of those proportions right at our population proportion of 41.2%. So the center, still the population proportion of about 0.412. And then the last thing we need to know is, as a whole, right on target. But again, if we just take a single sample, how close is it going to be to giving us the answer? How far away is P going to be from P hat? So if we look, on average, we're off by a little bit less than 5%. So our standard error this time is 0.049. The larger sample we took, the more reliable our statistics become, the more we can trust it to give us fairly accurate results. So again, I want to know, what are my chances if we just take one sample, this time of 100 apartments, of getting a sample proportion of 50% or higher? So if we look at our simulated 5,002 samples, that happened about 4.6% of the time. So the probability of getting a sample proportion greater than or equal to 50%, now that our sample size is 100, was this 4.6% that we got from the 5,000 samples. And since this is very bell-shaped, a normal model should give us something close to the same results. So the theory should match the practices, the idea now. Still centered at about 0.41. Our first tick mark will go up to about 0.46. The next one will go up to about 0.51. So we'll fall into this tail, shade the area above. That's the part that we want. If we go to second vars, scroll down to normal CDF, still 0.5, still 1,000, still a mean of 41.2. So 3 of the 4 numbers didn't change. Again, the only thing that changes is the spread. This curve got closer and closer to the center. So we'll change it from about 0.79 to 0.49. And we end up with a normal proportion of about 3.6%. 0.036. Sorry about that. So, again, not exact, but it's only off by 1%. Using this normal approximation for a sample of 100 apartments give us something really close to the actual percentage that we found in our data. So larger samples give us more normal results. And someone actually found this out a long time ago. If you ever heard of the Bernoullis, one of the Bernoulli cousins figured this out and came up with what we call the central limit theorem. And what it says is, if you take a large enough sample, a lot of your statistics will end up following a normal model that'll have these sample proportions, or sample means, will have these nice bell shapes to them. So what we can say, if we meet a few of our conditions, is that as long as our sample proportion will follow then a normal model centered at whatever the population proportion is. So it's going to be centered at the true amount, the number that we actually want to know. And in order to get the standard errors, though, we simulated them and just see how spread out they were. So what we would want to do instead is maybe get a formula for those. And this is the formula we can use to figure out what the standard error is. So for instance, when our sample size was 10, the standard error would be equal to the square roots of 0.41 times 1 minus 0.41 over our sample size of 10. And if we plug that into our calculator, if we plug it into our calculator correctly, there we go. So 0.41 times 0.59, 41% minus 100 gives you 59%. Divided by our sample size of 10, we end up with 15.6%. And if you go back, that's really, really close to the standard error we got just from repeatedly taking samples over and over and over again. StatCrunch isn't following any formulas, they're just doing things randomly. And it turns out our theory matched the results really closely. If we move on to a sample size of 40, what would the standard error be? So the top part of our fraction stays the same, so still 0.41 times 1 minus 0.41. But the difference now is we're going to divide by 40 in our denominator. So we can just put this part back in, change our sample size from 10 to 40, and we end up with almost the exact same amount that we got from those 5,000 samples. We have 0.079, now we get 0.078. The theory matches the results. And then if we do it one last time for our sample size of 100, we should get something really close then to what we found up here of 0.049. So if we enter in 100 here, we end up with 0.049. Our formulas gave us the right amounts, or at least something really close. So as long as we meet a certain number of conditions, we can use the central limit theorem, the most important theory in statistics, to give us the results of what our sample proportions we can expect to look. So what are those 4 conditions? So what we need in order to use the central limit theorem to figure out what probability model we're going to use to mimic the shapes that all these sample proportions would take is essentially we kind of have 2 big ones. We need a large enough sample size, and how we check to see if our sample size is large enough when we're dealing with a categorical variable, when we're interested in calculating proportions, is we'll take our sample size of n and multiply it by the population proportion. So when our sample size was 10, we multiply that by about 0.41, and we end up with about 4.1, which isn't greater than 10. So in that case, we wouldn't meet this part. And we also have to do n times 1 minus p. So we can kind of consider this how many successes we could expect to get. Now, if we take a sample of 10, how many of those apartments would we expect to be in Brooklyn? Which we'd expect around 4. And this is going to be the number of failures we can expect to get. And in order for the normal approximation to be close, in order for these two to give us similar results, we need to expect at least 10 successes and 10 failures. We need both of them to be greater than or equal to 10, which in our sample size of 10, we didn't make it. We had 4 and 6, both of which are less than 10. If we move on to a sample size of 40, if we want to see if we meet our sample size condition, we take n times p, which is 40 times 0.41, which will give us about 16. And then if we do n times 1 minus p, that would be 40 times 0.59, which would give us about 24. Both of those are at least 10, so that means we would meet our sample size condition. And if we look back, we end up with something pretty similar, 16.3% to 13.3%. Again, not an exact match, but because our sample size was large enough, the simulated proportion and the theoretical proportion matched up. So we need to make sure our sample sizes are large enough, otherwise the sample proportion may not follow a normal model. And then the next big one is what we call independence. We need to make sure each apartment we're picking doesn't influence the result of the next apartment we're going to pick. So this kind of goes back to that definition of independence we had in chapter 12. So we want the first apartment to not influence the result of the next apartment or the next apartment or the next apartment. So there's two things we can check for to see if this independence assumption is true. The first thing that we want is we want to make sure that our sample size is less than 10% of the entire population. So we took a sample size of 10 apartments, 40 apartments, and 100 apartments. Looking back, there was a total sample of 40,000 apartments. 10 is less than 10% of 40,000, 40 is less than 10% of 40,000, and 100 is less than 10% of 40,000. So you just want to make sure your sample size isn't more than 10% of the entire population you're pulling from. Well, usually we don't know what our population sizes are. So we'll kind of look at it the other way. We know what our sample size is. We usually know what n is. So we'll take n, multiply it by 10, and as long as we can reasonably believe the population is at least 10 times our sample size, we'll say this condition is true. Like if I didn't know how many UVM students there were, but if I went out and took a sample of 100 of them, I take 100, multiply by 10, get 1,000, and as long as I believe there are more than 1,000 UVM students, we meet our 10% condition. And then the last one we need is our randomization condition. We just want to make sure that we're taking random samples from the population. Later on when we get to chapter 17, 18, 19, and 20, we could do random assignment, but for chapters 13, 14, and 15, we're going to assume that we have a random sample taken from the population, which is exactly what we had StatCrunch do. Just pick 10, 40, or 100 apartments completely at random from our population. So if you meet these two conditions, they form together to make our independence assumption. So there's really only three things you need to check. Large enough sample size, and when we're working with proportions, a success-failure condition, and we need to make sure our sample size isn't too big, and we want to make sure that we took a random sample from the population that we're trying to learn about. And if all of those are true, then we can use this normal distribution to kind of model what we would expect to see for our sample proportions. So in order to figure out that first question at the very beginning of how often, if you take a random sample of 10 apartments, you'll get 50% or more of them in Brooklyn, you have to figure out every single possible combination of 10 apartments you could get, which can't really feasibly do. But we can shortcut it and meet these three conditions, we can replace it with a normal distribution instead. And it makes life a lot easier when we can do that, as we're going to see when we get to confidence intervals in the next section.